Hello everyone and welcome back to Wild True Learn. In the first episode we did the first few levels and we left off before doing decision trees. But before we get into this level, I wanted to take a look around the UI because I think there are some very interesting things that we haven't explored last time. On the top right here we have different percentages, which I saw last time, but I think what they mean is the first one, cat speech recognition system at 13%. I think this is my overall progress in the game. So if the first 4 levels are 13%, that means the entire game has about 30 to 35 levels. The second percentage, recognizing cat on pictures at 71%, I think is my progress in this current section. So when this gets to 100, maybe we'll have another story segment coming up. Over here we have task type. Last time all our missions are purple, which are almost machine learning. And as I noted in the discussion video, they are just very simple tutorials on basic programming. They're not really machine learning just yet. But this time, when we get to decision trees, it's going to be basic machine learning. Over here we have a sticky note. Eliza World's first chatbot, so cute. And in the background I see kind of like a printed circuit board design, but it's also shaped like a tree. The tree is kind of reminiscent of the branching structure of our levels here, which is really cool looking. Okay, I think we can go back and there's stuff. Whoa, there's a lot of stuff behind here. Okay, that's me, I guess, sitting on my chair. Here's my snowman, here's my cat. Whoa. Oh, it purrs too. Oh, I love that. I love that. Okay, I've got a cactus here. Okay, what is this? This looks like some kind of machine. Oh, I can change the window. Okay, I like the nighttime one. That's my money day menu. Okay. Clock. Oh, I can turn the light on and off. Let's turn it back on. Snowman doesn't do anything. I can open the drawer. Okay, wait. Here's, I guess that's pizza. That's a soda can. Snowed coffee cup. Okay. Oh, wait, what? What was that? No, come back. There you go, little buddy. That's a little raccoon. It's cool. I can change my screen too. Oh, this one looks good. Looks like I'm staring at a blue screen of death. Okay, let's go to our inbox. These are our completed tasks. No startups yet. We have an email though. The history of expert systems. 1965 can be considered our starting point for the work on creating expert systems. That year, scientists of Stanford Research Institute Edward Feigenbaum and Bruce Buchanan teamed up with Nobel laureate Joshua Lederberg and began working on a computer system designed to determine the molecular structure of chemical compounds. Yeah, that's a nice little bit of backstory there. Determining the molecular structure of chemical compounds is also a very interesting use of machine learning. Okay, we got, oh, these are things we can buy. Allo does nothing, has TESV SkyROM pre-installed, mandatory for purchase. What? Okay, I guess we'll buy that. A bunch of other stuff that I can't buy yet. Nodes, isolation forest, random forest, gradient descent. These are processing nodes that I can buy to speed up processing, I guess. Hardware, cat skins. Only a few find the way, some don't recognize it when they do, some don't ever want to. Get a cat. Oh, this just opens a browser window. Okay, no, I don't want your marketing. 2 flower. Okay, this is also a browser window, but it has some promo codes in here. Okay, we'll get back to that. this one I can't buy that yet. So let's pat our cat some more. Oh, am I sleeping? Okay. Yep, I guess that's it. Okay, let's start the missions then. Decision trees. Hey, is there any way to detect the cat without using expert systems? It works for text, but with pictures not so much. Furthermore, that cat just won't sit still. That it does not. Try decision trees then. Those are like expert systems but on steroids. Once you feel comfortable around them, try Sift. This little devil is way more effective with pictures. Also works nicely when paired with other algorithms. Or you can use nails or glue or something. Come on, it's just a cat, it won't fight you back. Oh, I dare you to fight a cat. You are not going to win. Just kidding, please don't use anything I mentioned on an actual cat. Different nodes have different processing rates. This parameter will influence the efficiency of your schemes. Icons on the right indicate the amount of time. Yep, already saw that. Decision tree color in the game. Okay, looks like it's splitting red and blue, but the green ones, okay, the green ones can come on both lanes because it's not being sorted. This node compares output parameters to sockets with an element's color. If the element's color is equal to only one socket's color, the element moves to that socket. If an element's color satisfies both conditions or none of them, it goes to a random socket. In the real world, decision tree is one of the basic machine learning algorithms. Each tree knows a limited number of classes. For each element, the tree asks some questions and chooses the class most similar to the element. Okay, so red, green, and blue, we want red and green here, green and blue. Okay, so that's just a basic decision tree tutorial. That's how it showed in the tutorial. Okay, yep, perfect. Okay, let's go do the side mission. Optimization. Hi, it's us again. We hope it's our last request for you. We've changed our database system. Yeah, see, I told you. You're gonna come back and say, we changed everything. Can you rewrite the program for us? Can you update your code one last time? We need it to work faster. Okay, to increase and decrease speed, click a button on the screen or use... Okay, yeah, we already did that. It's already maxed out. Red, green, and blue, we want red. Okay, so normally we were using expert system, but I'm guessing because this takes 1 second as opposed to 0.3 seconds, this is going to be too slow. So decision tree, we can sort by red first, but the problem is this is going to, there's no way to get both blue and green on this lane. So whatever we do, some of the greens are going to leak over to the first lane. So we're going to do another one to filter out the green. So this first level is going to filter out all the blue ones, but some green ones might still be mixed with the red. And then second level will throw away all the green ones, that leaves all the red. That should work. Okay, great. Release. Okay, and then Medx. Greetings, our company is manufacturing all organic, natural painkillers. They are used to decrease suffering, mood improvement, and coping with eating disorders. Yeah, I think we all know what all organic, natural painkillers you're doing. No side effects, including dilated pupils, diarrhea, physical and mental addiction, are caused by the human factor. From time to time, our workers pick the wrong plants. Yep, because they look like medical herbs. We'd like you to design an algorithm that would sort herbs by petal color. Okay. So, red, green, and blue. We want red and green and blue, and more red and green. Okay, so let's do this. This will give us red and green on top, and then green and blue on the bottom, and then we just want to split the red and green. Okay, so let's do this, and then we can do any so that there's no decision criteria, and then we'll just split them across the two outputs. Let's test that. Okay. Release. Oh wait, we only got a silver medal. Hold on. We might be able to do this better. We want the gold medal, right? Oh, I see. They have different time requirements. We have 25 seconds. How long did this take? Yeah, we're running out of time. Oh, I see. This one was filling in too slowly. Okay, so this one requires 19 blocks. This one only requires 15. So yeah, we probably need to find a way to get more blocks over to the top. So we can't split it like this because it'll split evenly. Okay, what if we did... Let's try something like... Okay, what if we did this? So all the red and green ones we keep as before. Oh, whoops, this is supposed to be any. Okay, so we had this node like we had before, where all the red and green ones get split. And then out of the blue ones, we want some of the green ones to get split over to the top. So this one's still going to get blue and half of the green ones, and this branch is going to get the remaining green ones to make up for the difference. And we have the most green blocks from our input, so that should be faster. Okay, great, very nice. Save and exit. Okay, we got another email in our inbox. Who invented the decision tree? Decision tree is one of the automatic data analysis methods. The first ideas of creating decision trees date back to the works of Hovland and Hunt in the late 50s of the 20th century. However, the fundamental work that gave impetus to the development of this direction was a book named Hunt, Marin, and Stone Experiments in Induction, published in 1966. Okay, let's get back to our tree. Crowd psychology. Decision tree equals smart tree. Yeah. Okay, I can't do this yet. I guess I have to do these first. Okay. Illuminati origins. Good day. I study ancient manuscripts and books in order to figure out the true story behind the Illuminati secret society. I need to recognize all the triangular shapes in these documents to solve the puzzle. Could you design a program that would do that for me? Sure. Sift. In the game Sift, I guess it goes by colors now. By shapes, I mean. This node compares shapes. If an element's shape matches the designated shape, the said element goes to the top socket. Others go to the bottom socket. Okay, so this is like your regular, the first node that we got for doing colors, except this does shapes. In the real world, SIFT, Scale Invariant Feature Transform, is one of the most powerful non-neural algorithms for detecting features on pictures, which is essential for image recognition. SIFT is very fast and is capable of recognizing simple objects and patterns. Okay, we got different shapes. We just want triangle, so triangle goes over here, trash can. Okay, great. Not too bad. Startups. Working for the man feels too easy, boring, or soul-sucking? Aim for the sky and become a CTO of a startup. In the world of savage market loss, it's either sink or swim. Will you get rich or bite the dust? It's worth trying anyway. Okay. Pizza Smith. Mama Smith's Pizza Shack. Hello, we are honored to invite you to join our startup, the world's first AI-controlled pizza place, but our fingers are always stained with flour and we can't really code because of that. Help us write and implement an algorithm that would be capable to separate orders for round pizza from orders for square-shaped pizza. Who eats square-shaped pizza, you heathens? Let's feed the people and become rich. Okay. The scheme created while working for a startup does not differ from any other, but there's no solution to startups. The scheme just works better or worse, and your future profits depend on its quality. Okay. Yeah, so okay, this one doesn't have metals. I guess you just try to make it as good as you can. So you have the round ones, you have the square ones, you only have round ones or square ones. This is... I don't think you can make it any better than this. It's as simple as it gets. Your program seems to be working fine. Further testing won't affect your results in the startup. Feel free to stop testing now. Okay. You're trying to design an AI-controlled pizza place. It serves pizza in round and square shapes. The scheme you're designing is the brain of the pizza robot. It sorts orders by the shape of pizza that your clients order. These are the users of your startup, in this case your pizza restaurant. They've heard of a new amazing place in town and now they want to grab a slice. These are your clients' orders. The millennials don't care too much about toppings, only shape matters. Mind the accuracy. If a client gets a pizza they've ordered, they will pay you money and tell their friends about your place. If a client doesn't get what they want, they refuse to pay and don't expect them to return with friends. One more thing, clients don't like waiting in queues and they will leave with no hesitation. If your scheme is working slowly, the waiting line will get longer. The market is constantly changing, so pay attention to what's going on and experiment with your schemes. And now it's time to launch your first startup. I guess we'll just release information. This action deploys the code to the servers from this moment. The startup will work automatically, okay? This table is your principal source of information about your startups. Press next day to proceed. Pizza Shack, income, users, balance, hype. Time is money. When you switch to the next day, you get the money you've earned or lost depending on how many users' requests were processed by your scheme. Press next day. Like, share, subscribe. Hey look, your users seem to like what your scheme is doing. They're even inviting friends. The cash is flowing. Press next day. So do I just keep going? All about hype. When hype icon is green, that means your startup is all over the news. Expect lots of new users. Okay, so I just keep going. Do I... Today share cost 600. Are you sure you want to sell them and leave the startup? No, not yet. I guess I'm still getting new users. Do I just keep pressing next day? It looks like I'm getting less users than before though. Okay, I get more cash. I get 1637. Time is passing by and the market changes. When hype icon is yellow, it means your target audience is already aware of your startup. Don't expect many new users at this point. Okay. When hype icon is gray, that means you've satisfied your target audience. Users starting to leave. Watch your earnings carefully. When the number becomes red, it's time to cash out. Press next day button to proceed. Okay. So right now there's no more hype. Can I patch? Circle, square, yeah, they still want the same thing. Looks like it's working. Okay, I don't think that makes any difference. Do I just keep pressing next day? Okay, I'm getting more users, it looks like. Okay, now I made $22.50 this month. That's good. Okay, cool. That's weird if I just Do I just keep going until... Oh, okay, this is going way down. Income is going way down. I'm thinking next day it's gonna get negative. So maybe it's time to cash out. 21.54. Let's try one more. Okay, yeah, it's negative. It's still 21.54 though. Are you sure you want to sell them? I guess so, because we're not making money anymore, right? Okay. We got something new in our inbox again. A letter from Mom and Dad. Ooh. Hello, dear. We remember how you cherish your financial independence, but come on, your birthday is just around the corner. Be a good kid and take the money and buy yourself something nice, will you? We love you very much and we miss you. P.S. Do not forget to put a hat on. It's very cold outside. Take the cash. Okay. And then we can buy new stuff. We have our aloe. Cactus protects from radiation. I don't know if that's true. Banhammer miniature. We can't buy that yet. That's pretty expensive. We can buy new hardware though. Increases sockets processing queue by 3. Increases data transfer speed by 1%. Rentium increases nodes work speed by 1%, increases data transfer speed by 1%. Okay, I don't know if these actually affect your processing or if they're just doodads on your table. Okay. Oh look, yeah, it looks like I got the, whatever this is, the Rentium. Oh, this is the tambourine. Where's the raccoon? Yeah, we have to have the little guy. Okay. Tree. Okay, let's do... Yep. Let's do chicken escape. Chicken escape farm. Hi there, my name is Sarah. I own a small technology farm. Our distributors demand supplies of eggs of different kinds, and it takes a lot of time to sort them manually. That's why we've decided to automate the process. We have all the data about eggs parameters, but we need an algorithm which will work without human assistance and with high accuracy. Okay, so just sort the different shapes. Okay. Oh, 1.238, so yeah, it did change the processing time of our nodes. Okay, we're only allowed 2 nodes, so it looks like this is going to be it. We can sort by circle, and then by square, and by triangle. That should be it. Uh-oh. No, that's only a silver medal. Looks like we almost got there. Maybe it's just random? Or you know what? We have the most squares, so I'm wondering if we should... I guess maybe it doesn't matter. I don't know. If we do squares first, and then the rest... Try like this. I don't think it's gonna make a difference, because either way it's gonna... Yeah, see, now the circles are a little bit slow. The triangles. Okay, maybe we want the triangles to be the fastest, because there's fewest of them. So as soon as we get a triangle, we want it to go there as quickly as possible. Okay, great. guess we'll finish this before we get to the story segment. Crowd psychology. Good day. Our company is making a research on crowd psychology. We need an algorithm which would be capable of defining a person's type based on certain behavior patterns. This way, we will be able to quickly identify dangerous individuals in the crowd and prevent unpleasant accidents. We have identified the parameters to work with, but we need an experienced developer to write an algorithm. Okay, now we got shapes and colors. Nice, okay. So we only want... Okay, this is starting to get complicated. We got the decision tree color and we got the sift. So we want, okay, first of all, red and blue, but we also want red squares over here, huh? Okay, let's try. Okay, yeah, first of all, let's try triangle, because only the bottom receives triangle. The rest will have to receive everything else, but we're not done here, obviously. Only the bottom receives triangle, but we only want green triangles too. Ooh. I don't want to use too many. Okay, maybe we go by color first. So we have a red that can potentially go into both outputs. So we want blue on top and green on bottom. That way blue and red end up here, green and red end up here. So now blue and red going here, but we want to filter out all the triangles because we don't want those in our output. Okay, so now the top side is going to get all the blue and red things that are not triangles. Okay, so that should satisfy the top. And the bottom now is going to get green and red, but we need to sort the green and red colors. So we have green and red, and for each one we want a different shape. So greens, we only want triangle. We're going to trash the rest. And then for reds, we only want square. And then we're going to trash the rest here as well. Okay, let's try that. Okay, that wasn't very efficient, I guess. Okay, so one thing I'm noticing is because the sift is way slower than decision tree, see it's 1.23 seconds compared to 0.29 seconds, which is more than 4 times slower. Because it's so slow, all these inputs are getting stuck here and it's not able to process very efficiently. So maybe we should start with sift after all. Maybe we should start, let's clear all this, start by sorting shapes. So like we had before, let's sort out the triangles. So now we have, oh wait, no, that's not right. Let's sort by circles. All the circles have to go on top. all the triangles and squares don't necessarily have to go on top. So all the circles go on top. We'll put more stuff in there later. And then we'll sort by triangles. All the triangles necessarily go on the bottom. And everything that comes out here is going to be a square, and square can be either one. Okay, next up, circles. Oh, I just thought of something. Yeah. Okay, let's go by color now. We want red and blue to be on top and some of the red to be on bottom. So maybe red and any. How would that work? Okay, here's an idea. Output stream 3 can accept green triangles and red squares, but the red square is annoying because it also shares the output with stream number 1. So if we look at output stream number 3, it only requires 18 inputs, and we have 20 green triangles. So if we send all the green triangles this way, then that's going to satisfy this output. We don't even need to send any red squares over here. And what we can do then is send all the green triangles down here and send everything that's not green and not a triangle up here. And that should make it much easier to separate the inputs instead of trying to send the red squares in both directions. So let's start with a shape. Oh, actually, if you look at this, it takes 1.23 seconds to classify each shape, and we require 22 plus 18, that's 40 items total. 40 times 1.2 is going to be more than 43 seconds, so this is definitely not going to work. We can't just use sift as the first level, because then every single input is going to get stuck here, and it's going to take way too long to even process the first layer. Okay, so that means we have to start with a decision tree color. And what I'm thinking is we're going to do that classic setup where we filter out all the red and blue up here, and then we're going to leave the green down here. So red, green, blue, and green. Okay, like this. So all the red and blue are going to go up here. Down here we're going to have some green and blue where we separate them with a second decision tree. So all the blue still goes up here, all the green still goes down there. Okay, so now we have the colors sorted out. Next we need to sort by shape. So green we only want triangles. Only want triangles here, trash the rest. And then out of the red and blue ones, we want to reject all the triangles. So again, let's connect that. Triangles. We want to trash all the triangles and accept everything else. Okay, let's give this a try. Okay, this one's getting stuck again. I think it might be too slow. Yeah, a little bit too slow. Okay, what we can do is, since we are allowed one more node, how about we process these in parallel? So instead of sending both of them to the same sifter, which is the problem we had before where decision tree is very fast. They're sending in all the inputs this way. All the inputs are getting stuck at the sifter because the sifter is so slow. So we want to separate the payload a little bit and let them process in parallel. They're going to do exactly the same kind of processing. and then send their outputs to exactly the same places, but now we have two of them working together. That should make things faster. The first one's still getting stuck, so maybe we'll try to optimize that. Oh, no, looks like it's getting there. Yeah, cool. That was a pretty challenging level, actually. Accept, and okay, looks like we have finished everything, gotten all the gold medals, up to the next story point. So this is a pretty good place to end the gameplay. Keep watching if you want to hear a bit more about decision trees and stuff, or if you just want to see more gameplay, then you can go ahead and skip to the next episode. The puzzles in this episode use decision trees, and you've no doubt noticed that their behavior is quirky. For an object that it's not trained to recognize, it can classify them into either one of the outputs. So why does it do that? Well, remember that decision trees are just a series of questions about the input. Here's the example for classifying rocks again. You or the computer can use the answer to each question to follow the decision tree and reach a result. But notice the questions here only make sense if you're actually looking at a rock. If you're not looking at a rock, let's say you're using this chart on an apple, and you follow this decision tree, then you get essentially a random answer that has nothing to do with apples or rocks. And you'll get different random answers depending on what you're looking at. If it's a beehive, a keyboard, a cookie, they'll each be classified as a different kind of rock according to this decision tree. And that's what the game is simulating. When the decision tree only applies to red and blue things, then giving it a green object, which it doesn't know anything about, and the questions are not going to apply, is going to produce random nonsense answers. So that's it for this episode. Thanks for watching, hope you enjoyed, and see you next time.